Welcome to this comprehensive guide on function notation. Today we're going to explore one of the most important concepts in mathematics, function notation, commonly written as f of x. Function notation is a powerful method of expressing relationships between two variables in a concise and clear manner. Instead of lengthy written explanations, we can use this elegant mathematical shorthand. This notation replaces the traditional y equals format. Instead of writing y equals 3x plus 1, we write f of x equals 3x plus 1. Both represent the same mathematical relationship, but function notation provides additional clarity and flexibility. Think of a function as a mathematical machine. You put an input value x into the machine, and it produces an output f of x according to a specific rule. The letter f is simply the name we give to this particular function. Throughout this video series, we'll explore why function notation is so valuable, how to evaluate functions properly, and common mistakes to avoid. By the end, you'll have mastered this essential mathematical tool and understand why it's used throughout advanced mathematics. Function notation offers several key advantages that make mathematical communication clearer and more organized. Understanding these benefits will help you appreciate why mathematicians prefer this notation system. Imagine you're working with multiple equations that all use y as the output variable. This creates confusion because you can't easily distinguish between different mathematical relationships. Function notation solves this problem by giving each function its own unique name. Now we can clearly distinguish between f of x, g of x, and h of x without any confusion. Notice how each function has its own letter name, f, g, and h. This makes it crystal clear which mathematical relationship we're referring to at any given time. The second major advantage is that function notation immediately identifies the independent variable. The variable inside the parentheses tells us exactly which variable is the input to our function. This works with any variable name, whether we use t for time, u for a general variable, or z for a complex number. The function notation makes it immediately clear which variable is independent. The third advantage is that function notation clearly specifies which element of the function we're examining. When we write f of 2, we know exactly that we want the output when x equals 2. This precision eliminates ambiguity. We can calculate f of 2, f of -1, and f of 0 as completely separate and distinct values, each clearly labeled. While function notation is the most common, there are alternative ways to express functions. We have standard f of x notation, mapping notation using arrows, and set notation using ordered pairs. However, the standard f of x notation remains the most versatile and widely used because it combines clarity, simplicity, and mathematical precision in a format that's easy to read and understand. In summary, function notation provides the mathematical community with a clear, organized, and precise way to communicate about functions, making complex mathematical ideas more accessible and less prone to confusion. Now that we understand function notation, the next crucial step is learning how to evaluate functions. Function evaluation is the process of finding the output when we know the input. Think of a function as a mathematical machine. You put an input value into the machine follows its rule, and produces an output value. To evaluate a function means to substitute a specific input value for the variable x in the function's expression, then calculate the result. Here's our step-by-step process. Suppose we have the function f of x equals 3x minus 5, and we want to find f of 4. Step 1, we write f of 4 equals, then copy the function's expression, replacing every x with 4. Step 2, now we perform the arithmetic. First, we multiply 3 times 4 to get 12. Step 3. Finally, we subtract 5 from 12 to get our final answer of 7. This means that when the input is 4, the output of function f is 7. We have successfully evaluated the function at x equals 4. Now let's try another example to reinforce this process. Consider the function g of x equals x squared plus 2x minus 1. We want to find g of -2. Following our process, we substitute -2 for every x in the expression. Now we calculate each term. -2 squared equals positive 4. 2 times -2 equals -4. And we still have -1. Finally, we add and subtract from left to right. 4 plus -4 equals 0, and 0 minus 1 equals -1. The key to evaluating functions is careful substitution and following the order of operations. Remember to use parentheses when substituting negative numbers or complex expressions to avoid errors. Now that we understand function notation, it's crucial to recognize and avoid the most common mistakes students make when working with functions. These errors can lead to incorrect answers and confusion, so understanding them will help you master function notation more effectively. The first and most common mistake is thinking that f of x means f times x. This is completely incorrect. The notation f of x does not represent multiplication at all. Instead, f of x represents the output value of the function f when x is the input. Think of it as the function's value at x, not multiplication. The second common mistake involves incorrect substitution. When evaluating a function, you must clearly show each step of the substitution process. Many students jump directly to the answer without showing their work. This makes it impossible to check for errors and doesn't demonstrate understanding. Instead, always write out each step clearly. First substitute 4 for x, then perform the arithmetic operations step by step. This approach helps prevent errors and shows your mathematical reasoning. The third critical mistake involves forgetting parentheses when substituting negative numbers. This error completely changes the mathematical meaning and leads to wrong answers. Without parentheses, negative 3 squared equals negative 9 because the exponent only applies to the 3, not the negative sign. With proper parentheses, negative 3 in parentheses squared equals positive 9 because we're squaring the entire negative 3. Always use parentheses when substituting negative numbers or expressions. The final common mistake is ignoring the order of operations. When evaluating functions with multiple operations, you must follow PEMDAS or GEMDAS carefully. First, substitute 2 for x. Then follow order of operations. Calculate exponents first, then multiplication, and finally addition and subtraction from left to right. By avoiding these 4 common mistakes, you'll be much more successful with function notation. Remember that f of x represents a function's output. Always show your substitution work, use parentheses with negative numbers, and follow the order of operations carefully. Now we'll work through our first example of evaluating a function. This will show you exactly how to apply function notation in practice. We have a linear function f of x equals 2x plus 5. We need to find f of 4, which means we want to know what output this function gives us when the input is 4. Step 1. We substitute 4 for every x in our function, so f of 4 equals 2 times 4 plus 5. Step 2. We perform the multiplication first. 2 times 4 equals 8, so we have f of 4 equals 8 plus 5. Step 3. Finally, we add 8 plus 5 to get 13. Therefore, f of 4 equals 13. This demonstrates the key process of function evaluation. We took our input value of 4, substituted it into our function rule, and followed the order of operations to get our output of 13. The function machine took in 4 and produced 13. Remember, this same process works for any linear function and any input value. The key is careful substitution and following the order of operations. Now we'll work through a more complex example involving a quadratic function. This will show you how function notation works with polynomial expressions that have multiple terms. We have the quadratic function g of x equals x squared minus 2x plus 1. Notice this is a polynomial with 3 terms: a quadratic term, a linear term, and a constant term. Our task is to find g of 2w. This means we need to substitute 2w for every x in our original function. We substitute 2w for every x in the function. Notice that we put parentheses around 2w wherever we substitute it. This is crucial to avoid errors, especially when we have exponents or coefficients. Here we can see each place where x was replaced with 2w in parentheses. The first term becomes 2w quantity squared, and the second term becomes negative 2 times the quantity 2w. Let's work through this expansion step by step. We start with our substitution, where every x has been replaced with 2w in parentheses. In step 2, we expand the first term. 2w quantity squared equals 2 squared times w squared, which gives us 4w squared. Remember, when we square a product, we square each factor. In step 3, we simplify the middle term. Negative 2 times 2w equals negative 4w. We multiply the coefficients. Negative 2 times 2 equals negative 4, and we keep the variable w. Our final answer is g of 2w equals 4w squared minus 4w plus 1. This is our completely simplified result after substituting 2w into the original quadratic function. Here are the key points to remember when evaluating quadratic functions. Always use parentheses when substituting expressions to avoid sign errors. When squaring a term like 2w, remember to square both the coefficient and the variable. And when distributing, multiply coefficients carefully to get the correct signs and values. This example demonstrates how function notation works with more complex algebraic expressions. The key is careful substitution and systematic simplification of each term. Now that we've mastered the fundamentals of function notation, let's explore how this powerful mathematical tool applies to real-world situations that we encounter every day. Consider how a person's height changes over time. We can represent this relationship using function notation, where height depends on age. For example, if we know that a 10-year-old child is 50 inches tall, we can write this as f of 10 equals 50. This notation clearly shows the input age and the corresponding output height. Another practical application involves calendar functions. We can create a function that tells us how many days are in any given month. For instance, March has 31 days, so we write f of March equals 31. Similarly, February has 28 days in a regular year, so f of February equals 28. Function notation appears everywhere in our daily lives. Temperature changes throughout the day, costs depend on quantities purchased, and distances vary with travel time. These examples demonstrate the versatility and power of function notation. It provides a clear, concise way to express relationships between variables in any field of study. As we conclude our exploration of function notation, let's review the key concepts that make this mathematical tool so valuable. First, function notation f of x provides a clear way to express relationships between input and output variables. It eliminates confusion and makes mathematical communication more precise. Second, this notation allows us to work with multiple functions simultaneously without confusion, using different letters like f, g, and h to distinguish between them. Third, function notation makes evaluation straightforward. Simply substitute the input value for the variable and calculate the result. Finally, function notation bridges pure mathematics and real-world applications, helping us model everything from population growth to financial calculations. Mastering function notation opens doors to advanced mathematics, including calculus, statistics, and mathematical modeling. It's a fundamental skill that will serve you well in any quantitative field. Thank you for joining me on this journey through function notation. If you found this tutorial helpful, please give it a thumbs up and subscribe for more mathematics content. Leave a comment below if you have questions about function notation or suggestions for future topics. Keep practicing, and remember that mathematics is a journey of discovery. See you in the next video.